we're going to walk through this R script. Last time we did the QQ plot or quantile plots, and we created a random sample of X with a mean of 20 and a standard deviation of 4. And so I'm just going to go ahead and run that again. We'll plot the histogram, and we've got our sample of X. And notice I have density on the y-axis. That way I can plot probability density functions over that. The way to do that, again, is frequency equals false and the histogram function. We can plot a normal distribution over that. And there's the fitted normal distribution. So what we're going to do is use the chi-square goodness of fit test to see, is this sample in fact from a normal distribution? We know it is because we've generated it, but we'll use this chi-square test to do that. So we'll scroll down to part 4. And I'll just wait another minute for you all to catch up. For the chi-square goodness of fit test, we're comparing empirical or observed frequencies within a histogram to theoretical frequencies from a fitted distribution. We're saying, does this histogram represent that theoretical distribution? So the first thing we're going to do is calculate the frequencies within each of our histogram bins. And I think in this case, we're going to be comparing our histogram, which is actually a sample from the normal distribution, to the normal distribution. So the first thing we'll do is we'll create an object that stores the histogram. It's not going to plot it. And so I'm calling that X hist. And so I'm just saying, run a histogram on X, which is our sample, and store it as a histogram. So if you look at that, we get this object over here, and it's got the breaks, which is a vector of just where we're breaking the data for the bins. That counts the number of observations in each bin, density, midpoints, etc. Okay, we'll extract the values of the bin because we're going to use that to sample the normal distribution and actually create, the area under the curve for that. We'll get our counts out. So that's going to be our observed frequencies or observed counts. And then our K value, which is the number of bins. All right, so we've got the information we need for our observations, our observed frequencies. Now we need to calculate the theoretical frequencies using those same bins. So we're just slicing up the normal distribution at each of our bins and then calculating the area under the curve to get our frequencies or percent of total area. So right now I'm just going to be, this is just to create the normal distribution, just to kind of plot it. And this is the cumulative distribution function for that normal distribution using the same mean and standard deviation as before. And you can see these are where the bins are. So what I did is I said, draw some lines where our bins are, where we would have our cumulative distribution function at that. Yeah.
For the X, the sequence 0 to 40, how do you select those values?
Oh yeah, so that's based on our sample. How did I determine that? If you look at our X, and I can just do this, I'll do range X. And that gives me the range of my X values. So I look at my sample, and this is really just a plot. This is really just visualization right now. But I want to make sure I cover that range.
So that's why it's like 0 to at least 11.
Are you saying about this big X sequence? Right, so it starts at 0 and it goes to 40, but my observations fall in this range, and this is the range of the histogram. So what these red lines are showing is the cumulative probability values of my histogram bins. So what I did is I just took the bin values, so X bins, and if I go back to the histogram, you'll see that the bin starts at 10, it goes all the way up to 28. but this is each side of the bin. So it's the dx is 2, so 10 to 12, 12 to 14, 14 to 16. And then what I did here is I said, okay, now let's look at the cumulative probability on the normal distribution, the fitted normal distribution with the same mean and standard deviation. What are the cumulative probabilities of observing all of those? And so these red lines, actually, let me let me just go through this and see if we get a better visual, and then we'll come back to it. Okay. Okay. Oop. So what we're doing here is we're saying for each of those histogram values, bin values, what is the cumulative probability? And that way I can say, okay, from 10 to 12, I get this difference right here, and whatever this difference is going to be the expected frequency. So from 12 to 14, this is the expected frequency. From 14 to 16, right? I expect to see more observations. Ultimately, when we get up here, say this is 0.5 and this is 0.7, my expected frequency would be 20% of the observations should fall in this particular bin. And then it gets smaller as we go out into the tails. So AB line, yeah, plotting stuff, right? AB line, we'll just do question mark AB line. You've got a lot of options with AB line. You can do A and B, which is slope and intercept, and draw just a line, like a regression line. Or you can do H, and this is a horizontal line, and you just give it the H values. Or V, and that's going to just do vertical lines. So you give it X values, and it plots a vertical line at the X values. So I just did H, and I gave it Y values, which were the frequencies, or cumulative probabilities. Okay, so now we've got, based on the bins from my histogram, we have the cumulative probabilities, and if we just subtract the two, we get the expected frequency or probability that we would see from the normal distribution in each bin. And so we'll look at that in a second. So I'll just zoom in here. So what we're saying now is we're starting at 10, and with that cumulative distribution function, I'm calculating the area under this curve, under the normal distribution, but just by subtracting this cumulative probability from this cumulative probability. All right, now we're going to use the difference function to extract the expected cumulative probabilities. Or sorry, in this case, this is just going to be counts. So what I did is I said, give me the cumulative probabilities, which is this. And then the maximum is about 20%, like I said, in the middle. So we expect 20% of the observations. And then I multiplied it by n. So now I'm going to get an expected count with each bin. So if I sum those up, that should be close to, it's not going to be exact, but that should be close to my n, and my n was 25. You can see right here. So that's working, it's not perfect. And now I have, with this, a vector of expected counts, and I can compare that to my observed counts. And you can see this was 5 and 5 in the middle, and this is about 5 and 5. So doing okay so far. This is about 1 over here. This is 0, and this is expected to be 1. So there's a little bit of divergence there. And then now what I'm going to do, and this is just the visualization exercise, I'm going to plot my histogram. I'm going to calculate the midpoints, which I think I could actually just extract directly from the histogram. So this was a little bit of didn't need to do that. If you look at this, the histogram has a function or a vector of mids. So I can just say this would be X hist mids. So that'll be a little bit better. And then I'm going to use the segment functions, which just plots line segments. You need to give it X and Y values, and it will plot line segments for you. And I'm going to plot the theoretical counts on the histogram. So if my fitted normal distribution would expect to see this many counts for each histogram bin based on the theoretical distribution. So that's just the visualization. Observed frequencies on the histogram in gray, and then expected frequencies in red. Okay, so now we'll do the chi-squared test. We did our kind of our observations of stuff. We'll do the chi-squared statistic, and so we're just summing the differences between observed and expected squared divided by expected. And so that test statistic ends up being 3.848. We'll calculate our degrees of freedom, which is the number of bins minus 1 minus the number of parameters in the distribution we're testing. So we're doing the normal distribution, so it has 2 parameters, mean and standard deviation. And then we'll do this chi-squared function. So Q chi-squared. Q just means quantile. If I put a probability in there, it gives me the chi-squared value or the test statistic. And so what we're doing is putting a critical, we're calculating the critical chi-squared test statistic here. So this is the chi-squared test statistic, above which we would have a 5% probability of seeing a value for which the distribution is actually the same, of our observation is actually the same as the theoretical distribution. So let's look back at this right here. So this is the critical value that we're calculating here based on the degrees of freedom. The value of chi-squared that has a 95% probability of exceedance, or I guess of non-exceedance. And it needs the degrees of freedom. So that's the one parameter that the chi-squared distribution needs. And so this is our critical value. Let's see. There we go. So our critical chi-squared value for these degrees of freedom is 12.6. And we'll note that our chi-squared value from our sample is less than that. So if you go back to the drawing, we are way over here. We were about, I think it was 3.4 or something, 3.5. And so we cannot reject the null hypothesis. We have to accept it. We can also calculate the probability of seeing that chi-squared value, the p value, and we plug our chi-squared value in, we give it the degrees of freedom, and we're subtracting from 1. So the probability of seeing that is 0.75, and that's just a really that's a really high probability, meaning it's very likely that our sample came from the normal distribution. We'll get into evaluating p-values next week. All right, and then we'll just visualize this, and I won't run through the code, but here is the chi-squared distribution for this particular problem. Here is where our chi-squared statistic fell, and then here's the critical threshold, the 95% significance level. So we're way over here. We do not reject the null hypothesis. We say, yeah, this did come from a normal distribution, or we can't reject our null hypothesis that they're not different. So not surprising. And then the last thing I'll say is if we were over here, what that means is we have a 5% chance that so if we're over here, we're going to reject the null hypothesis. We're going to say, well, with a 95% confidence, our distribution from our sample is different from the normal distribution. So we reject the null hypothesis, accept the alternative hypothesis. But we still have that 5% chance that it in fact came from the normal distribution. So that's the type 1 error. We'll talk about that a little bit. What that means is it's a very low probability that our sample came from the normal distribution, but it's not a 0 probability. It's a 5% probability based on this test, based on this setup. So that's that threshold that we'll talk about. Okay, we will be using this code in the project. So that's why I wanted to introduce it here. So we'll see this again, but you can use the same code.